Okay, in this lecture we're going to finish our section 3.2 material on the theory of second-order linear homogeneous equations. And in this last part of the section we're going to introduce a result known as Abel's theorem, which is a useful theorem which allows us to determine the general form of the Wronskian for a set of two solutions of some homogeneous second-order equation without actually having to find the solutions. That is, we can find the Wronskian directly from the differential equation. So let's take a look at this theorem. This is theorem 3.2.6 from your textbook, and this result is known as Abel's theorem. And here's what it says. If we have two solutions, y1 and y2, of the second-order homogeneous linear differential equation, which here is written in standard form, where the coefficient functions p and q are continuous on some open interval I, then the Wronskian for a set of solutions, y1 and y2, of that differential equation is given by some constant c times e raised to the negative integral of p of t dt, where c is some certain constant depending on which two solutions of the equation we're working with, y1 and y2. And moreover, this Wronskian is either 0 for every value of t if our constant c is 0, or is never 0 if our constant c is non-zero. So let's take a look at the proof of this theorem. Let's see why this expression is going to give us the Wronskian for a set of two solutions. So first off, let us recall what the Wronskian of a set of two solutions, y1 and y2, of a second-order linear equation is defined as. So we saw it is given by the determinant of the 2 by 2 matrix, where our first row of this matrix is the functions, y1 and y2, and our second row would be the derivatives of those functions, y1 prime and y2 prime. So taking this determinant, we have y1 times y2 prime minus y2 times y1 prime. So if we differentiate this expression for the Wronskian with respect to t, we know the Wronskian is a function of t, so we can find its derivative. And we have for our derivative, by the product rule, we would have a y1 prime, y2 prime, plus y1 times y2 double prime. And then we are subtracting, again by the product rule, we would have y2 prime, y1 prime, plus y2 times y1 double prime. So we see that a couple of terms cancel here. In particular, y1 prime, y2 prime, and minus y1 prime, y2 prime will cancel. And so we are left with our derivative is equal to y1, y2 double prime, minus y2 times y1 double prime. Now we know that y1 and y2, or in the theorem statement we were supposing that y1 and y2 are solutions of this homogeneous second-order linear equation. So where I have these two expressions for y1 and y2 double prime, well, we can solve for y double prime in terms of the lower order derivatives using our equation. This equation, if we solve for y double prime, is equal to negative p of t times y prime minus q of t times y. And since y1 and y2 are both solutions of this equation, y1 and y2 double prime are given by this expression that we've just solved for. So if we substitute that in, we have our derivative of the Wronskian is equal to y1 times y2 double prime, which would be negative p of t, y2 prime minus q of t times y2. And then we were subtracting y2 times y1 double prime, which is equal to negative p of t, y1 prime minus q of t, y1. And in this second term, since we were subtracting a negative value, well, we can make all these subtractions of negatives, positive values, addition of some positive term. And then we see a couple of other terms are going to cancel here. In particular, the y1 times y2 minus q of t and the y1 times y2 plus q of t terms cancel. And so we are left with our derivative of the Wronskian is equal to negative p of t y1 y2 prime plus p of t y2 times y1 prime. So if we factor out a negative p of t from each term, we are left with positive, since we're factoring out the negative. We have a positive y1 y2 prime minus y2 y1 prime. So this expression that we're left with after we factor out our p of t term is exactly the definition of the Wronskian for these two solutions, y1 and y2. So we have our derivative of the Wronskian is equal to negative p of t times the Wronskian itself. Now what we're left with here is a separable differential equation for the Wronskian. So to solve this, we could use separation of variables. If we put everything with a w on our left-hand side and everything with a t on our right-hand side, we have the following. And then we can integrate on both sides to solve. So our antiderivative on this left-hand side is the natural log of absolute value of the Wronskian w, which is equal to the negative integral of this p of t function with respect to t. And so solving for our Wronskian, oh, and let's see, let me not forget my plus c to have our most general antiderivative. We have some constant on the end there. And so to solve for our Wronskian, we exponentiate on both sides, giving us some constant times e raised to the negative integral of p of t with respect to t. And when we look at this expression that we have for the Wronskian, well, this e to the negative integral of p of t dt can never be equal to 0. So the only way that this Wronskian could possibly be equal to 0 is if our constant of integration, c, or this constant out in front, c, was equal to 0. So here we can say that our Wronskian is equal to 0 if and only if our constant c is equal to 0. So this establishes our result, known as Abel's theorem. And again, this theorem gives us a way to find the Wronskian of a set of solutions for some second-order linear homogeneous equation without actually finding those two solutions. So we know the general form of the Wronskian for any solutions of such a differential equation. And one thing I want to mention before we look at some examples of applying this is that this formula that we're using in Abel's theorem, which involves this function p of t, relies on the fact that p of t is the function that we're looking at when the equation is written in standard form. So as we've seen with a lot of these different equations, we need to first make sure that our equation is written in standard form so that we can make use of this formula that we've derived in Abel's theorem. So now that we have this result, let's look at some examples making use of it. In this next example, we are asked to find the Wronskian of two solutions of the following differential equation, which we can see is second order, linear, and homogeneous, without solving the equation. So without actually finding two solutions, find the Wronskian. So right away, we know we want to use Abel's theorem. Abel's theorem will allow us to find the Wronskian for a set of solutions of a differential equation without actually solving. And the first thing that we need to do to apply Abel's theorem is rewrite the equation in standard form. So here, to put this equation in standard form, we need to divide everything through by cosine of t, the coefficient in front of our y double prime term. So this would give us 1 y double prime plus sine of t divided by cosine of t times y prime minus t divided by cosine t y is equal to 0. And now we're ready to apply Abel's theorem. Using Abel's theorem, we know that the Wronskian for a set of solutions, y1 and y2, of this equation, which would be functions of t, has the form some constant c times e raised to the negative integral of p of t. And looking at our equation in standard form, we see that the function p of t is this sine t divided by cosine t. And now we need to find our antiderivative of this function. So to find an antiderivative of this sine t over cosine t, or it's the same as tangent t, we can make use of a substitution. If we choose u as our denominator, cosine t, then du would be negative sine of t dt. And so rewriting our integral in the exponent in terms of u, we are left with the integral of 1 over u du. So for our antiderivative, we have e raised to the natural log of absolute value u, or substituting u back in, we have e raised to the natural log of absolute value cosine of t, which gives us c times the absolute value of this cosine function. And depending on which t interval we're working on, cosine t could take either positive or negative values. So the positive or negative, we could group with our arbitrary constant c out in front and write this as c times our cosine of t function. So here we have the general form for the Wronskian of two solutions of this differential equation. It's given by some constant times cosine of t. Now let's look at another one. In this last example, we are told, or we are asked, if a differential equation shown here, which is second order, linear, and homogeneous, has a fundamental set of solutions, y1 and y2, and the Wronskian for those two solutions at time t equals 1 is given as 2, find the value of the Wronskian for that same set of solutions at time t equals 5. So again, in this problem, we're being asked about a Wronskian for a set of two solutions of a homogeneous second-order linear equation, and we're not told what the solutions are. So if we're asked about the Wronskian without finding solutions, we know that we want to apply Abel's theorem. And again, to apply this theorem, the first thing that I need to do is rewrite my equation in standard form. So to put this thing in standard form, we would need to divide the equation by t, the coefficient of y double prime, which would give us y double prime plus 2 over t y prime plus e to the t times y is equal to 0. And now we are ready to apply Abel's theorem, which says that our Wronskian for a set of two solutions, y1 and y2, which are functions of t here, is equal to some constant c times e raised to the negative integral of p of t. So looking at our equation in standard form, we see that our p of t function is 2 over t and here we can integrate directly. We have some constant c times e raised to the negative 2 natural log of t. So if I bring the negative 2 into the argument of my logarithm, I have c times e to the natural log of t to the negative 2. And so I'm left with c times t to the negative 2 or if you prefer as a fraction, c divided by t squared. So now I need to find the value of this constant c. And to find the value of c, I can use the information that I was given about the value of the Wronskian at time t equals 1. I was told when t is equal to 1, this Wronskian equals 2. So applying that condition, the Wronskian for this set of solutions at time 1 would be equal to c, and we were told that value has to be 2. So our Wronskian for this set of solutions, y1 and y2, at time t, is equal to our constant 2 divided by t squared. And once we have this Wronskian, we can evaluate it at any other time. Here we were asked about the value at time t equals 5. So if we substitute 5 in for t, we have 2 divided by 5 squared, so 2 over 25 would be the value of this Wronskian at that time.